Alrighty, so now you guys are starting sequences of rigid transformations. You have learned to translate, you have learned to rotate, you have learned to reflect, and now you are going to learn how to perform those in sequences. Alright, and with your everyday language, sequence, right, one thing happens, and then another thing happens after that, and then another thing happens after that. Okay, and that's kind of how it applies to rigid transformations, right? You can perform a transformation, then perform another, and then another, and so on and so forth. Okay, so it says we have three triangles here: triangle BWN, triangle B prime W prime N prime, and triangle B double prime W double prime N double prime. And that's how you would say that there. All right. Number one asks you to describe the feature of triangle B prime W prime N prime, which is this triangle here, right? What is unique about this triangle that indicates what kind of rigid motion was applied to triangle BWN? All right, so all they're asking here is what is special about this triangle that shows you what kind of transformation was applied to this triangle. So I want you to go ahead and stop and think about what kind of transformation, okay, that could have been. All right, so let's be logical about it. All right, well, we know this couldn't have been translated, right, to this triangle because the orientation is not the same anymore. Okay, the triangle, the way it lays on the grid here, is just not the same anymore here. All right, so we know it could have been translated. We know that it probably wasn't reflected either because the only logical way to reflect that triangle to get there would be over the line y equals negative x. And that looks like this. Remember that line, y equals negative x. All right. But even then, if we reflected this triangle over this line, right, where would B prime sit? Well, B prime would sit somewhere here. W prime would sit somewhere over here. All right. And same with N prime. It would sit somewhere over here if we reflected it. So we know it wasn't reflected. So the only logical thing we're left with is to think that it was rotated, right? All right. And remember, whenever you're rotating shapes or something on a coordinate grid, you're either rotating around a fixed point, and if they don't give you a fixed point, then you can assume that you're going to rotate around the origin. And in this case, it's P. All right. So if we rotate this triangle around the origin, all right, well, remember, the image points must sit equal distant from the origin as its pre-image coordinates were. All right. And one way to show that is you can think, it looks like B is a very specific distance from the origin. All right. And if we rotate it around the origin, all right, well, how would we get from B to B prime? Well, you'd get there, and it looks like B prime, if I drew B prime to the origin, it looks like it's the same distance as B was to the origin. And look what we kind of made here. We made a 90-degree angle. All right. And to get from this point B to B prime, it looks like you would have rotated 90 degrees counterclockwise. All right. Because we're going this way counterclockwise. All right. And the same thing applies to W and W prime. All right. And I'll do this with a different color. Looks like W is this exact distance from the origin. All right. And it looks like after it was transformed, right? And again, we're assuming it was rotated. Well, look, the distance remained the same from the origin. And again, I'm just eyeballing it, but it appears that it remained the same. And again, it looks like it was rotated 90 degrees counterclockwise that way. All right. So we can assume that this triangle was rotated to get to triangle B prime, W prime, N prime. All right. So number one asks you to describe the feature of this triangle. Okay. Well, what did we conclude? All right. We can say the distance of the image vertices, right, from the origin remained the same. All right, we can say the distance of the image vertices from the origin remained the same, but the orientation changed, indicating a rotation was done. All right? Alrighty, so now that you have that written down, let's look at number 2. Number 2 asks you to describe the feature by mapping the transformation of one vertex of triangle BWN onto B prime W prime N prime. Well, it looks like we already did that, right? We mapped one vertex, we took W, we mapped it onto W prime, we indicated it was a rotation. More specifically, a 90-degree rotation, counterclockwise. All right, so now we're just going to complete the table. What kind of transformation did we perform? We performed a rotation. But let's be more specific. What kind of rotation? Well, we did a 90-degree counterclockwise. 90-degree counterclockwise. All right, and what is our algebraic description for a 90-degree counterclockwise rotation? Right, if you take a look on the whiteboard, you will see what that is. Your XY coordinates will flip and your Y will become negative, right? And that's just your algebraic description for a 90-degree counterclockwise rotation. All right. Let's look at number 4. Okay, number 4 says map the transformation of one vertex of B prime W prime N prime onto the triangle B double prime W double prime and N double prime. All right. So from this triangle to this triangle. All right. And when you first look at it, you can assume, or you can see that the orientation is the same. They lay the same way. Okay. So whenever you think about it logically, what kind of rigid motion was performed, you would probably guess it's a translation. It's just a translation, all right? So let's map one vertex, and I'll take N here just because it's the neatest in this area. Let's map N prime to N double prime, all right? And to get there, it looks like I have to go to the right 1, 2, 3, 4, 5, 6, 7. All right, and then I have to go one more. Oh, no, it looks like, no, I don't. Looks like I'm stuck there, and then I just go down 1, 2. So I went to the right 7, so I added 7. And then I went down 2, so I subtracted 2. Went down 2. And in a sense, we kind of just made the algebraic description for the N prime point to N double prime point. Okay, so what did we do? Okay, remember we said it was a translation. All right, and how can we describe our translation? Well, my XY coordinate, which was N prime, okay, it changed by how much? Well, my X, I went to the right 7, so x plus 7, and it looks like it went down 2, okay? Y minus 2. That's how much my x and y changed. All right, let's look at the back. All right, it says triangles RKH and BYT are shown on the coordinate grid, where RKH is the pre-image. Okay, so this is the pre-image, and that's, I'm assuming, the image. All right. It says describe the feature of triangle TYB, right? So what's special about this triangle that indicates that more than one ridge of motion was applied to triangle RKH? Okay? So what's unique about this triangle that shows me that I have to get there through a sequence of transformations? Okay? So one way to think about it is it possible that we translated this triangle onto this triangle? And at first glance, okay, there's no way, all right, because the orientation, right, the way this triangle looks here doesn't look the same here, okay, it just doesn't look the same, all right? So we can't say that it was translated, okay? What about reflected? Was this somehow reflected to get there? Well, again, the only logical way to think about it is that it was reflected through the line y equals x, okay, which is this line here. But again, if that was the case, well, it looks like r prime would have to sit somewhere over here. Looks like h may have fell onto y, but k would have fell somewhere over here. Okay, there's no way we could have reflected it over the line y equals x. All right, and then we have a rotation. Is it possible that this was rotated? All right, and one way to think about it, all right, is to see where our points can fall onto it when we rotate it from the pre-image. All right, what I mean by that is, well, take a look here. It looks like h is this far from the origin, right? We're rotating around the origin. Okay, so we rotate h. Okay, it can either go counterclockwise or it can go clockwise. All right, but when we do so, it's going to look something like this, right? H could only go somewhere around this circle because, again, we're rotating around the origin. And it has to stay the same distance the whole way around, okay, from the origin, no matter where you rotate it. All right? So it looks like H may have fallen, it probably can fall onto Y, okay? But whenever you look at the triangle, okay, H and B are corresponding coordinates, not H and Y, okay? H does not fall onto Y, it falls onto B. All right, one way to think about it, R must fall onto T, K must fall onto Y, and H must fall onto B. All right, if this was the pre-image of that triangle. All right, and the same thing applies to point K, okay? And I'm going to erase this here just so you can see what I'm talking about. All right, K is this far from the origin, okay? So if it rotates around the origin, okay, K can only fall somewhere, and I know it's not going to be perfect, but K can only fall somewhere around this circle, okay, somewhere like this. And I know it's not perfect again, okay. Maybe it would have fallen onto T, but remember, K and T are not corresponding coordinates, okay. So that's just one way to look about it, or look at it. All right, so let me get this cleaned up here. All right. So how would we describe the feature of TYB? How will we describe that more than one ridge of motion has to happen? Well, I can just say the general orientation of triangle TYB does not support the idea that only one rigid motion was performed to triangle RKH. All right? And I know like looks like a K there, but that's an R. RKH. All right, so it says draw triangle R prime K prime H prime as a result of the first transformation. Okay, so what can we do to get this triangle to map onto this triangle? Okay, well, the logical way I would go about it is, well, I notice that if I were to reflect this triangle over the x-axis, the orientation of this triangle would look like this one. All right, so again, we wouldn't want to translate it first because it would still look like this, and we need it to look like that. Okay, so I would reflect it over the x-axis. Okay, so if I did so, h, which is at -1, 1, would be at -1, -1 down here. Okay, and again, I'm reflecting over the x-axis. I'm reflecting over this axis here. Okay, so h prime would be here. Okay, k, looks like k is at -4, 3. So if I reflect it over the x-axis, it needs to be the same distance on the other side. So again, -4, 3. So it needs to be, if it's 3 that way, it needs to be 3 down here. So it'd be at -4, -3, which I'm gonna try to eyeball it here. Eyeball this here. It looks hard to see. -4 would be somewhere there. All right, and that would be k prime. All right, and R, if I reflected R over the x-axis, the same thing. Okay, R looks like it sits at -4, 7. All right, now I reflect it over the x-axis. It needs to sit 7 units away from the x-axis. So 7 down here, still be at -4. So -7's down here. 4 looks like it'd be there, and that would be R prime. Again, it looks like a K. R prime. All right, so my triangle will look something like this, and this, I have no excuse for it to not be a little bit more perfect. Okay, my triangle will look something like that, and you can see that the triangle now lays in the same orientation as this triangle. They look the same. Okay, so before we move on, I need to point something out very important to you. Okay, we have now created a new pre-image of this triangle. Okay, so whenever you talk about this triangle now, you can essentially forget about this triangle up here. This triangle no longer matters. Okay, this is the new pre-image. All right, so whenever you are referring to it in the future, now you would say that the pre-image of triangle TYB is this here. All right, and you actually notice that they refer to it differently. Up here they refer to it as TYB, and here they refer to it as BYT, and you'll see why that's so in a minute. All right, so we already did number 7. We did it right here. Okay, now it says map the transformation of one vertex of R prime K prime H prime, which is this triangle we made, onto BYT. All right, and again, why did they change the way they named the way they named the triangle? Up here was TYB, now here's BYT. Well, they did that because R prime is now going to match up with B. Okay, you see R prime will match up with B. K prime will match up with Y. K prime will match up with Y. And H prime will match up with T. Okay, H prime will match up with T. So that kind of hints at me that I could just grab this triangle and move it over here and put it on top of there, and it would be congruent, to be equal to that triangle. All right, and I guess I kind of already hinted at it. We're just gonna translate this triangle now onto that triangle. All right. So we only need to map one vertex, so I'll choose R because it looks the neatest here to do. So to get from R prime to B, it looks like I have to move to the right. 1, 2, 3, 4, and then one more time 5. So I went to the right 5, so I'm gonna add plus 5, and then I have to move up 1, 2, so plus 2. All right, and I kind of just did our translation algebraic description there. So now we're just gonna map. We're gonna complete the table of what we just did here. Okay. So what was my first transformation? Well, I reflected over the x-axis. So reflection over x-axis. All right. And remember, I have an algebraic description for that. When you reflect over the x-axis, what happens to your xy coordinates? Your xy coordinates, they stay the same, but your y becomes negative. Right? And that's just the algebraic description there for that. All right. And then what was our second translation? Okay. Once we got this triangle, we then translated it. But how much? We went to the right 5, and then we went up 2. So our second transformation was a translation. All right. And what was our algebraic description for that? How did my xy change? All right, my xy, my x moved to the right by 5, so I added 5 to my x value, and it went up 2, so my y value went up 2. All right, and that's all that would be there. All right, so we have this last question, number 10. It says, explain how to know if the sequence of transformations preserves distance. All right, and I want you to stop for a quick second. Think about how you would answer that. Alrighty, so one way you could have thought about it, okay, was that, well, you know that reflections and translations are rigid motions, okay? And what are rigid motions? Well, rigid motions are transformations that preserve distance, okay? So preserve distance, what does that mean? Well, it means when I reflected this triangle, okay, the lengths, the sides, right, the lengths of the sides did not change. And then when I translated it, it also did not change, all right? So I know that the transformations we performed preserved distance. Okay, but how do we know? What's another way of showing that they preserve distance? And this is precisely why you learned how to do distance formula yesterday. All right, so I suggest you grab a scratch piece of paper, right? That way you can follow along with me as we show that the transformations, the sequence of transformations, they preserved distance, okay? Because we are about to perform midpoint formula. So I'll let you go ahead and grab a piece of paper. All right, so let's start on this. All right. So I'm going to cut this down just a bit. All right. We are only going to solve for the distances of the triangle R prime, K prime, H prime, okay, this triangle, and then compare that to the image triangle, okay, and to see if the lengths of the sides stay the same, right? Hence they preserved distance. All right. So let's do that. All right. Well, first I need to find out where R prime, K prime, H prime, where they lay. Okay, where do they lay? So where does R prime lay? R prime lays at, what is this? -4, -7. If I'm seeing that right. -4, -7. All right. And I guess I'll scoot this up here because we don't need all that. That way we have space. It looks like K prime sits at -4, -3. K prime sits at -4, -3. And it looks like H prime sits at -1, -1. So H prime sits at -1, -1. So what we're going to do here is I'm going to find the distance between R prime and K prime first, okay? So R prime and K prime, all right? And again, we're just going to apply our distance formula. So I guess this is going to be like another distance formula lesson here, all right? So remember, the distance formula is equal to the square root of the changes in X values squared plus the changes in Y values squared. All right, so we're just gonna plug in. Okay, so R prime, remember we're starting here, R prime, and I guess I'll give you some time to write that again. All right, R prime sits at -4, -7. All right, and this acts as my x1, y1 coordinates, right? My first set of xy coordinates. Looks like K prime, okay, sits at -4, -4, -3. Okay, and that acts as my second set of xy coordinates, x2, y2. All right, and we're just gonna plug this into the formula. Okay, and I'm just not gonna hold on to the variable d here, just because I know that this whole thing is gonna equal the distance. So I'm just gonna carry the square root. So let's plug in. So you should start with x squared, or I'm not x squared. I'm sorry, your x2. Okay, so which is -4. So if I just plug in, I should have -4. Okay, minus x1, which is 4 here. Okay, or I'm sorry, -4. So minus x1, which is -4. So we have -4 minus -4, and that's how you would write this. Okay, you need to make sure you're nice and pretty with your numbers. All right, and that whole thing is squared. Plus y2, which is -3 here, minus y1, which is -7. So -3 minus -7, and the whole thing squared. All right, and this is, you should have a calculator with you as well, just so we can do this. All right, so what do we get? Well, let's simplify. -4 minus -4 is the same thing as -4 plus 4. You can almost imagine this parenthesis makes a plus. So we'd get 0 squared, right? We get 0 squared plus -3 minus -7 is the same thing as -3 plus 7. And again, plus 7, that acts like as a plus, right? So you should get 4 squared, right? So then once we add all this, 0 squared is just 0, so I can forget about it. All right, what's 4 squared? Well, 4 squared is 16. So we have the distance from r prime to k prime is the square root of 16. All right, but we can further simplify this, all right? Because you guys know the square root of 16 is 4. All right? So, the real distance between r prime and k prime is 4 units, and we just don't know how much, but it's 4. So I can write that here. Okay? It is 4 from this to this. It is 4. All right, and I guess we'll just do the whole triangle before we move on to show that it preserved distance. All right, so what about k prime to h prime? All right, k prime to h prime. And I guess I'm going to write these coordinates here just so I don't forget where they are. So it looks like k prime is at -4, -3. This is at -1, -1. And this is at -4, -7. This is just for me to know where my coordinates are when I'm doing this without this here anymore. All right, I'm gonna fold this and make some space here just so we can keep using the same paper. All right. Okay, let's do k prime to h prime. Okay, we know k prime sits at -4, -3, and we know h prime sits at -1, -1. Okay. Now remember, I'm gonna write my distance formula here again. You don't have to write this if you already have it there on your paper, but I'm gonna write it just so you see what we're doing. Okay. So the changes in x coordinate squared plus the changes in y coordinate squared. Okay. So I'm gonna act like this is my x1, y1, and this is my x2, y2. All right. All right, so from the distance formula, we just plug in. Now we can just plug in. X2 would be -1, right? Minus x1, which is -4. So -1 minus -4. The whole thing's being squared. Plus y2, which is -1 here. Minus y1, which is -3. So -1 minus -3 squared. The whole thing squared. All right. So let's just simplify. Okay. We should get -1 minus -4 is the same thing as -1 plus 4. So you would get 3 squared. Okay. You got to hold on to that square. Plus -1 minus -3 is the same thing as -1 plus 3. So you would get 2 squared. All right. And if you just square these, well, 3 squared is 9, and 2 squared is 4. So 9 plus 4. So we get the distance between k prime and h prime is 13 squared. Okay, and we'll just leave it at that, because if you actually do that, you do 13 squared, or not squared, 13 square root, the square root of 13. If you square root 13, you get this nasty number here. We're just not going to do that. So we can say the distance between k prime and h prime is 13 squared. Square rooted. Okay, I don't know why I keep saying that. Square root 13, the square root of 13. All right. So now let's just do this line segment. Again, I'll just fold my paper one more time. That way I have some space here. Alrighty. So from h prime to r prime, what do we got? Well, we know h prime sits at -1, -1. We know that r prime sits at -4, -7. All right. And again, we're just going to plug into our distance formula. And I'm just going to write this here for for reference purposes. You don't have to write this. And we're just going to plug in. All right, we're just going to plug into the distance formula. So I can act like this is my x1, y1. And I can act like this is my x2, y2. All right, so once I plug in, okay, my x2, which is -4, minus x1, which is -1, so minus -1, the whole thing squared, plus y2, which is -7, minus y1, which is -1, minus -1, and the whole thing squared. All right. So let's just simplify. All right. We should get -4 minus -1, the same thing as -4 plus 1. So we should get -3 squared plus -7 minus -1 is the same thing as -7 plus 1. So we should get plus -6 squared. All right. So we know -3 squared, so -3 times -3 is 9. And we know -6 squared, 6 times 6 is 36. So 9 plus 30, 36. All right. So we get that the distance from H prime to R prime is equal to the square root of 45. And we'll leave it at that, because if we plug in and we square root 45, you get this nasty number here. So we're just going to leave it at that. So we can write that here. The distance from H prime to R prime is the square root of 45. And now all we're going to do is we're going to find the distances of these points. All right. We're going to find the distances, and we're going to compare them to that of the pre-image. And if they line up, then we showed that they preserve distance. All right. I'll leave this here for a quick sec while you copy that down. All right, so let's do the other triangle, the image triangle, okay? And I guess I'll try to speed this up here just so we make it in time. So it looks like B, or how do they refer to this triangle? BYT. So looks like B sits at, what is this? 1, -5. So 1, -5. Looks like Y sits at 1, -1. And I'll write that here. 1, -1. And then it looks like T sits at 4, 1. T sits at 4, 1. All right. And again, we're just gonna plug in. We're just gonna plug into the distance formula. So what is the distance from B to Y? Okay. Well, on this side we got 4. So if this is gonna fall onto here, this also needs to be 4. All right. So let's take B, which is 1, -5. Let's take Y, which is 1, -1. And again, I can act like this is my X1, my Y1. Again, I can act like this is my X2, Y2. And we're just going to plug into the distance formula, all right? And remember, I'm going to write that quickly here. You don't have to write this down. This is just for reference, so you see what I'm doing as I'm doing it. All right, so let's plug in. All right, so X2, which is 1, okay, minus X1, which is 1 squared, plus Y2, which is -1. Oh, I'm sorry, I wrote a plus here. That's not distance formula. It's supposed to be a subtraction here. Sorry about that. So Y2, which is -1, minus Y1. So minus negative 5 squared. Alright, so we'll just simplify. 1 minus 1 is 0, so 0 squared. So we'll have 0 squared here. And then negative 1 minus negative 5 is the same thing as negative 1 plus 5. And you should get 4 squared. Alright, so 0 squared is obviously 0, so 4 squared is 16. Alright, so the distance between B and Y, from B to Y, is the square root of 16. But we know what the square root of 16 is, alright? It's 4. So this distance is 4. And you kind of see, looks like if this triangle was translated onto here, this side is preserved. The distance is preserved. Alright? Let's do YT. Alright? I'm going to fold my paper here. That way we have some space. Alright. Let's do from Y to T. And again, I see where Y is at. Y is at negative 1. Or I'm sorry, 1, negative 1. And I see T, which I didn't write T down for some reason, is at 4, 1. And T is at 4, 1. So let's just plug into the distance formula. And again, I'm writing this for my reference here. Alright, this acts as my x1, y1, x2, y2. So let's just plug in. So x2, which is 4 in my case, minus x1, which is 1 here, squared, plus y2, which is 1 here, minus y1, which is negative 1. So 1 minus negative 1, whole thing squared. Alright, let's solve it. Well, 4 minus 1 is 3, so 3 squared is what I'll get. That looks like a 32. Let me make that a little neater. Get 3 squared. Alright, plus 1 minus negative 1 is the same thing as 1 plus 1, which is 2. Alright, so we get 2 squared. And again, we know what 3 squared is, and we know what 2 squared is. 3 times 3 is 9, and 2 times 2 is 4, so plus 4. So we get the distance from Y to T is the square root of 13. And again, look, it looks like it's matching up perfectly so far. We have the square root of 13 here, and that's the square root of 13. So we have one more to do. We just have this line segment left to do. I'll let you go ahead and catch up on that. Alright, so let's just do this last part, and we can show that that distances were preserved. They were preserved. Alright, so now we're just going to do from T to B, alright? And we know T is at 4, 1, and that's going to act as my x1, y1. We know B is at 1, negative 5, so B is at 1, negative 5. That'll act as my x2, y2. And I'm just drawing this for reference again, just so you see what I'm doing. Alright. So we just plug in. Okay. x2, which is 1 here, minus x1. So 1 minus 4 squared. Plus y2, which is negative 5. So plus y2, which is negative 5. Minus y1, which is 4. So negative 5 minus, not 4, I'm sorry. Minus y1, which is 1. So 5 minus 1. I guess let me make that prettier before it looks confusing. minus 1 squared. Alright, now let's just simplify. 1 minus 4 is negative 3. So we have negative 3 squared. Plus negative 5 minus 1 is the same thing as negative 6. So negative 6 squared. Alright, and then once we square them, negative 3 times negative 3 is 9. Plus negative 6 squared is 36. So we get that the distance from t to b is equal to the square root of 45. So from t to b, the distance is the square root of 45. And you can see here we have just proved using distance formula that the triangles, right, after its rigid transformation, they preserved distance. All right, the distance of each length are preserved, and we see that here. We have 4, square root of 13, square root of 13, and square root of 45, square root of 45. All right, and that's all. That's all for today.